Okay, while they're setting up, I'd like to introduce Taro Sekiyama, and who's going to present his work on temporal verification for answer effect modification with delimited continuations. So, take it away.
Yeah, thanks for introduction. And hi everyone. My name is Taro Sekiyama, and this is a joint work with Hiroshi at the University of Tsukuba. And the aim of this work is to verify linear time temporal properties of higher order programs. So first, let me review what is the temporal verifications in this setting. So temporal verifications aims to verify the temporal properties, and in this work we focus on especially linear time temporal properties, which specify the finite or infinite traces generated by programs. So one typical examples of temporal verifications is a resource usage. So in this example, I suppose there are three primitive operations to manipulate a file object, so open, read, and close. So the main function is a repeat read function. And first, this function starts with opening the file, and then reads the contents, and the read content is passed to the argument function here. And then this main function closes the file handler. And finally, it uses the non-deterministic choice here. And if this choice returns true, then the execution continues. But if it returns false, then the execution ends. And in this examples, first in this running examples, I use output functions as second parameters to the main functions. It's just print out the given string value. So, and a properties to be satisfied in this program is that it should file object. It should use a file object in a well-organized manner. So it means that if the program opens the file, it should close the file. Okay. And to formalize these desired properties, I suppose a special operation to raise event. So, here event operations raises some event, and here open functions raise the event open, read function raise the event read, and close functions raise the event close. Then the property of interest is formulated like this. In the trace generated by the program, every time event open occurs, then the event close must occur eventually, only once. So fortunately, this program satisfies these good properties because the trace of the programs, and we can check that the trace generated by these programs conforms to this either of two patterns. The first pattern is that finite repetitions of open, read, close, and the second pattern is the infinite repetitions of open, read, close. So because the program satisfies either of these patterns, because it's just open, read, and the read content passed to the argument, but it's just a print. So the control is returned to the main functions, and then file object is closed. So, and if at some time the non-deterministic choice returns false, then the trace conforms to the first pattern, and otherwise it conforms to the second pattern. But of course, the behavior of the programs depends on the second parameter to the main functions. So now consider the diverging functions, which raises some event x infinitely many times. Then the programs does not satisfy this expected desired properties, because after open files and read the content, then the content is passed to the argument functions, but it diverges. So before closing the file object, the control does not get back to the main functions. Okay, So this is the problems we consider in this work. And our aim is to extend our technique for temporal verification to higher order programs that can use first-class delimited continuation. So our motivations to support delimited continuation is that it is very powerful features to implement a variety of computational effects. So examples of computational effects include exceptions, backtracking, generator, first-order states, and so on. So by supporting delimited continuations, we can build a very generic verification framework for programs with computational effects. So, and our contribution is to provide a type and effect system to read about finite and infinite traces of programs with delimited continuations manipulated by the shift 0 and reset 0 control operators. And to express the behavior, to express the traces in effect system, we suppose dependent types, and actually effect can be value dependent in our effect system. And the important point from the perspective of the new effect system is that our effect system supports our dependent typing for continuation. So in our effect system, types of continuation can be dependent on the argument. As far as I know, this is our first dependent type system allowing this dependency. And we also implemented part of our effect system is implemented. And I mean that I implemented a constraint generator for our effect system, but yet we have not implemented the constraint solving. So it's just in progress. For automated verifications is in progress. Okay, in the rest of this talk, I will introduce our target control operator, shift 0, reset 0, and then explain the basic ideas of our effect system for temporal verifications in the presence of control operators. Okay, and shift 0 and reset 0 is just program operations. And to capture the shift 0 is operation to capture the continuations. And after capturing the delimited continuations up to the closest delimiters, the continuation is bound to X, and the body expression E is executed. And reset 0 is used to delimit continuations within the given expressions. And the key evaluation rule of these operations is this one. And it is combinations of shift 0 and reset 0. And here, capital E represents the evaluation context up to the closest delimiter from the shift operations. So it is captured as a function variable x, and x is replaced by the functional representations of the continuation E. And then the body of a shift is executed. So this is a key rule over shift 0, reset 0 evaluations. And one of the reasons we focus on this control operator is that it is a very good type systems, as I will explain later. And the second reason is that it is very expressive. For example, its expressivity is very similar to algebraic effect handler, which are recently popular constructs for structuring effects in programs. So I think shift 0 reset is has a good balance between the theory and practice. Okay, and so first I will show some examples of shift 0 or reset 0. And the first example is an exception. And here exception is implemented using option type. It has two constructors, none and some. And raise functions implement exception raising. And here raise just calls a shift 0 operation, and its body is a none. And yes, so this is examples of using this raise functions. So this is a very simple examples. It's just division functions. But if the second argument y is 0, it just raises exceptions. And the return value of division functions is wrapped by some constructor. And in this examples, first here function f is called with two number argument, and because the second argument is 0, raise function is called here. And then because its body is shifter operations, so the continuation colored blue is captured, but in the body of the shift does not use captured continuation. The continuation is just discarded. So it behaves like exceptions. Okay, and but supporting these very interesting operators, the temporal verification becomes more challenging. So this is an example, so revisiting the resource usage examples, but it uses exception raising functions in the second parameter to the main functions. And here the main function calls repeat read function calls the second parameter after open files and reading the content. So the generated trace should conform to the open read just two finite trace, including two events. So it does not. It violates the properties should be satisfied. So the temporal verification supporting delimited continuation control operators should find this program does not satisfy the properties. Okay, the second example of a control operator is backtracking. Backtracking, and here, yes, and this is the implementation of backtracking, and it provides three operations: choose, pair, sack, and choose just capture the continuation, and choose function is expected to return Boolean value. And after capturing the continuation, first the continuation is called with Boolean value true. So first the choose function tries to return the true value. But if the true value is not good for some computations, then it should return the none, and then it tries the second candidate Boolean value false. And if the computation is successful, then continuation should return some value. So the choose just returns some value to the closest delimiters. And fail and sack operations are implemented just returns none and some value after discarding the continuation. So I don't show the details of this evaluation steps, but here in this example, chooses some Boolean value x and y. Then it checks x or test is passed for given two Boolean values. And if the test is passed, then it is returned, and otherwise it is signaled as a failure. And then the final result is some constructor with Boolean values that pass the test, XOR test. And here, so this is a resource usage example with backtracking. And the second argument is f is implemented using choose functions of a backtracking. So first, after opening and reading the content, this choose function is called. Then, after closing the file handler, the non-deterministic choice is performed. And if this choice returns false, then the function call to the call to main function finishes. And then fail function of backtracking is called. And fail function means that this execution path is failure. So it resumes the programs from the point of the call, last call to the choose function. So the choose function is called this via the argument function. So the program resumes program is resumed from the here, and then it again the program tries to close the file handler again. So then this is the unexpected behavior. Okay, and so by supporting control operators, we need to track the control flows under these flexible manipulations of control operators, suspending, replacing, and resuming delimited continuations. So we need to reason about traces under such features. So to explain the more technical problems, so let me review this evaluation rule. Here, this evaluation rule, the reset the trace generated by these programs corresponds to the trace generated by the body of the shift expression E. Okay, and the trace generated by the function variable x, the continuation variable x, it corresponds to the trace generated by the continuations of shift expression, so capital E. So we need to, so it means that in type checking of the shift expressions, the type effect system needs to know what traces is generated by the continuations. And in type checking reset expressions, the effect system needs to know what shift operation is called in the body of the reset. So yes, and but this is not a specific this is not a problem specific to temporal reasoning. So actually, in the usual type system, we can find a similar problem. So in this case, the type of E, and should be matched with that. In this case, the type of the shift, the body of the shift reset expressions should be matched with reset expressions, and the return type of the continuation should be matched with the return value of return type of the continuations variables. So, and one way to address this situation is to use a type system that allows answer type modifications. So, answer types is used to propagate type information. And type system with answer type modification augment typing judgment with two kinds of types. So initial answer types and final answer types. And using these two kinds of types, the type system can check that the types that should be consistent is actually consistent. And we use this idea to temporal reasoning. And in this case, in our case, we extend and adapting answer type modification to answer effect modifications, because we want to reason about the effect. Traces represented by effect. And here, effect, and so types are augmented effect. And one kind of effect is the effect for traces, and the second kind of effects are for control operations. But in this talk, I skip the control effect. And value types also augmented with effect information. And in our setting, the effect of T specifies the traces of the expression E, and the effect of S specifies the traces of delimited continuations. And the effect of final answer effect B specify the traces observed as the closest delimiters. And using by this information, we can read about traces generated by programs with delimited continuations. And for example, event raising operations can be typed like this. Here, in the final answer types means that this operation means that if this operation is placed under some evaluation context, then the generated trace is event X followed by the trace of continuations. And similarly, for raise, for exception raising function, this effect can be provided. This means that the reset and the closest delimiter surrounding this the function call to this raise function observes just empty trace. So, in other words, observable at the closest delimiters are only events yielded before calling these raise functions. Okay, and and this mechanism is scalable to resume continuation multiple times. Okay, and yes, I didn't talk about something, but our effect system is dependent and dependent continuations is supported. Yes, and of course, which proves the soundness of the effect system. So it can correctly reason about finite and infinite traces. And several related works. And the point is that we are the first work that support reasoning about finite and infinite traces for programs with delimited continuations. Okay, and the key message is that answer type modification is very useful, not only for reasoning about values and reasoning about effects. Yes. Yeah, that's all. Thanks.
So we do have time for a few questions. Does anyone have a question?
Hello, I'm Stephen Ramsey from the University of Bristol. What can you say about inference for the system? So I know you said you built something that will generate constraints. So is this for inference? And do you expect to have some sort of conservative, or is there a fragment that's decidable?
Yes, and the inference is under development, and we can implement constraint generation according to the typing rules. But we need to solve constraints. We need to implement a solver for traces, and as far as we know, there is no solver on the traces. So it's under progress.
Okay. Do we have any other questions?
Hi, I'm Sky from University of Chicago. When you decided to use delimited continuations, without multi-prompts, do you think your work could be effectively analyze programs with multi-prompt delimited continuations, or do you think it's fundamentally different?
Yes, very good question. So actually, our development is based on a type answer type modification. But as far as I know, there is no type system that allows answer type modification for multi-prompt control operators. So, yeah, I'm not sure.
Okay. Any other questions? Okay. I'll exert some privilege here and ask you a question. So. One thing I noticed reading your paper was that the effects were like sets of traces of events, and this seemed very well suited to the way effect handlers give you an algebra of operations. Have you thought about adapting your work to support effect handlers?
Yes, it's our ongoing work.
Okay, thank you.
Thank you.
All right, let's have another round of applause.